Hello, everyone, and welcome to a no-nonsense discussion about life science data-intensive computing with Spark, presented by EMC. I'm Rebecca Friend, the publisher of the Life Sciences Group at Fierce, and I'll be moderating this webinar. Our speakers today are Sasha Pagel, Senior Business Development Manager at EMC, and Patrick Combs, Principal Life Sciences Solutions Architect, Emerging Technologies, also at EMC. And you can read their full bios on the right side of your window. I've got a few technical notes for you before we begin. If you have any trouble reading a slide, please hold and drag the right corner of the slide window to enlarge. Please also disable your pop-up blockers to participate in the interactive parts of the presentation. If you'd like to download a copy of the slides, please click on the Download Slide widget at the bottom of your screen. And we're going to be following the presentations today with a Q&A session, so please submit your questions during or after the presentations using that Q&A box at the right side of your window. All right, I think we're ready to begin. Sasha, take us away.
All right, thanks a lot. Let me get oriented here for a second. All right, hi everybody. As I got introduced, my name is Sasha Pagel. I look after the Life Sciences vertical here at EMC. And as you already know, I'm joined by Pat Combs. He's the principal architect for Life Science Solutions and Scientific Computing here. And what we wanted to do today is just a few things. One is really give a brief introduction to Spark, since that's actually getting a lot of interest across a variety of research organizations, whether you're in the life sciences or even beyond. And also share some initial sort of observations and best practices, based on our experience with a couple of, emerging tool sets, if you will, that rely on or leverage Spark. So today we're going to really kind of take a really big arc across the world of Spark. We'll explore the motivations for Spark, provide a brief introduction to what it is. We'll highlight a couple of really cool and interesting projects. One's called Thunder, another one's called Atom. Some of you already probably are very familiar with those projects, but they definitely deserve a mention. And then follow it up with just a discussion on some aspects about using Spark for data-intensive computing, based again on some initial lab work that we've done here. So let's get started with the motivation. And, oftentimes a lot of people are expecting us to sort of lead with talking about next-generation sequencing, but there's actually, a lot of activity, especially in the last year or so, that's going on in the world of microscopy in terms of analysis and what's going on there. And, why is that actually happening is just like the trends with how the chemistries and the instrumentation is changing in next-gen sequencing, the same thing is happening in microscopy. So really it's about, the detectors are getting, essentially bigger and faster. If you kind of dig into it, you really, from, let's see, looking back about now 10 years ago, data acquisition is about 1,000 times faster than it was, back in 2004. And now that's also allowing for a lot of new types of applications or methodologies to be put into play, and to be able to do things like neural recordings, on model organisms like zebrafish, or do experiments like or techniques like animal phenotyping, where you could have thousands of samples, and each sample can generate like 300 gigs of data. So the ability to acquire data and do it faster and more of it, presents some interesting challenges in terms of computing and analysis. And of course, here's my, the sort of the obligatory next generation sequencing slide. I think it goes without saying that, now with the X systems that have come out from Illumina, both on the instrumentation and the changes in the recent chemistries, data, if you're running at a full clip, you can generate 3 times the amount of data for a given, unit period of time. And this also, again, makes it, really opens up the possibility for, population-based analyses using next-generation sequencing. You already see this with, Scottish Genomes Project and the Genomics England Project, and there's various other national projects, and even here now emerging in the U.S. To really be able to sample and observe populations at scale. And of course, that also presents some challenges in terms of being able to interact and mine that data. All right. So you kind of step back and you speak to those groups that are actually doing this work. There's a few sort of common challenges, whether it's in the world of microscopy or in the world of next generation sequencing, and even proteomics for that matter. It kind of really boils down to a few sort of common areas. Now it's not uncommon for groups to operate at the petabyte scale. And the file data that's generated by the instrumentation in the given discipline often doesn't lend itself to compression very well. Also, moving that data can be a bit of a challenge. Moving it from where it was actually acquired to potentially where it's actually going to be computed on. And these are things that are needed for especially for population-based analyses. The other thing here, especially in our world of life sciences, oftentimes, because the way data is generated, you could argue that the file formats are sort of driving this behavior where groups actually essentially hand stitch together their analyses, whether it's just through a shell script or using tools like Galaxy, but ultimately you're chaining together, really customizing by hand every analysis pipeline, and that can sometimes prove challenging in terms of time to completion for that analysis. And really, and also in some fields, you want to be able to interact with the data, almost in maybe in near real time in some cases. And you also want to be able to reset and reapply different parameters and be able to do comparisons between operations. And also the other few challenges here is just some of these analyses can run from hours to actual days. It's not, particularly if you're in the world of oncology, it's not uncommon to see some groups running analysis pipelines that might do joint variant calling that could take 10 or more days depending upon the compute resources available to you. And then that also plays into challenges thinking about how you structure your data so you can get through the analysis. So that kind of leads us to what's sort of that ideal state. Where would we like to get to in terms of being able to interact and mine this huge volume of data coming off of the sort of new generation of instruments. And so really groups want to be able to, you'd like to be able to do that interactive analysis, to be able to do especially exploratory work, because at the outset of a given study or experiment, you may not have a complete sort of experimental design, and so there is really no right analysis, and you want to be able to tackle the data from really sort of different points of view using different methodologies. The other ideal here is that you want to be able to sort of quickly slice and dice and be able to get subsets of the data. So some groups you'll hear them talk about BAM slicing, where you're taking a slice or a subsection of a particular genome. And the other thing here too is that you want to be able to do these analyses very quickly and also be able to do them at scale. All right, so taking all those issues into play and kind of starting to think about, well, how can we do this differently? The Berkeley AMP Lab has started working on something called Spark for a few years now, probably 5 or more years, I think it is. And so they've introduced something called Spark, and Spark is really a general purpose computation framework. It's sort of a generalized version of MapReduce, and it has some really nice attributes to it in terms of being able to scale. It also affords fault tolerance, and then also be able to do a lot of computations in memory. So this kind of starts to tackle those challenges around latency. And also, particularly in areas where you have, one method chaining into another, and you also want to be able to apply different parameters to it, it enables or opens up the opportunity for interactive analysis. And, the sort of the key attribute or the key concepts behind, behind Spark really lies in the RDD or let me back up for a second. So we'll come back to the resilient distributed data set in just a second, but we also wanted to just call out very quickly, how would you actually take advantage of sort of the Spark execution environment. And there's a couple ways you can actually do that today. One, you can actually run it in a standalone mode and typically have sort of static resource limits assigned to it. And in other cases, you could actually, run it in with, say, for example, in a Hadoop or interface with HDFS and have Yarn do the resource allocation for you, whether it's sort of from the cluster side or from the client mode. And we'll come back to that probably when we get to the more of the discussion in terms of sort of managing resources and the execution. But what I wanted to do very quickly is take a moment and talk about the RDD. And so, what is the resilient distributed data set? And really, it's the core concept for the Spark framework. And probably the way to think about it is almost as a table in a database, and it can hold any type of data, and ultimately you can store that data in various or different partitions. And so the RDD lets you rearrange computations and also optimize processing of that data. And the RDD also enables essentially some fault tolerance. So if you something gets corrupted, essentially you can recreate an RDD and recompute the data sets. And ultimately that's because the RDDs are immutable. And you can really, but that said, you can also do transformations on those RDDs. And when you do a transformation, it ultimately derives a new RDD, and the original one actually stays intact or stays the same. And there's really sort of two types of operations on the RDD. There's transformation, which I just mentioned, and then action. And transformations actually don't return values, but they actually return a new RDD, and nothing's actually evaluated. It just returns a derived or a new RDD. And an action actually does the evaluation and returns a new value for that RDD. So that's really kind of at the heart of what's really behind Spark is this notion of this resilient distributed data set. A couple of other things to probably note here. Talked about the transformation, but the key thing here is that you can interface a variety of different types of file types, text files, sequence files, a lot of different input formats. In fact, if you're still kind of in the world of using HDF5 for scientific computing, there are now ways to, say, using Python to actually transform HDF5 into RDDs. The other thing that I failed to mention that I forgot about, another key attribute about Spark, besides the fact that you can essentially do most of the computations in memory, is that Spark also provides an API. So that opens up opportunities for developers to create new analysis applications. And also you can interface with Spark with tools like Scala, Python, R, and not have to actually worry about, say, the particular format of that data set. All right. So we'll move on to the next one. And another attribute about Spark is that it also allows for the use of different libraries, and sort of by default, Spark comes out of the gate with libraries to support streaming of data. So this is really kind of geared towards sort of real-time analysis. There's also libraries for SQL, and you can do sort of lazy evaluations where you can sort of make trade-offs between sort of accuracy and speed for your queries. You can also there's libraries for machine learning, and you can even incorporate outside libraries, and that kind of actually now brings us to our sort of, some of the example cases or use cases of what other groups are doing. And so if you look at the world of microscopy, there's a whole new sort of application area called light sheet imaging. And out of the Howard Hughes Medical Institute, actually out of the Genelia Farms campus, that team there actually developed a toolbox called Thunder. And so Thunder actually provides a lot of different tools for multivariate analysis, specifically targeted to neuroimaging. You can do things like clustering, factorization, and especially, a lot of these types of experiments are usually over a period of time. So time series statistics. And then there's also some utilities in terms of for sort of managing and manipulating the data. The other key, attribute here is that, you can actually, operate, Spark in a standalone mode, and actually connect to, say, an NFS resource, or you could actually interface with HDFS. And if you actually check out this Nature Methods paper, which came out last July, it makes a really great illustration of how that can be done and comparing sort of time to process some of this light sheet data. All right. And another example from Berkeley AmpLab is the ADAM project. And probably the way to think about this is really a tool set for mapping, alignment, and variant calling. ADAM being kind of the sort of the primary platform for that. There's some additional sort of tool sets that ride atop of it, but there's really sort of three parts to it. There's an API for actual sort of doing the transform, analyzing, and querying of data. So think about ADAM itself providing those capabilities. And the other sort of two things that come along with ADAM is also leveraging something Parquet for columnar storage. And so this again starts to address those challenges in terms of managing data at scale, and then also dealing with data types via Avro. And this is actually really this particular group is generating quite a bit of interest in their ability to be able to process data quickly, and then also be able to do some new and unique ways in terms of variant calling of that particular data. And I highly encourage you to actually check it out, whether it's this paper here, the primary paper referenced here, or actually go to GitHub and check out the actual tool set itself. So, but now in the last few minutes here, what I wanted to do is just kick off a discussion with Pat, since we've taken a look at both Thunder and ADAM in our labs, and just kind of explore some of the initial sort of observations and best practices using Spark to compute on any one of these data types. So, Pat, if you can just chime in here. Let's see if you can. You're still dialed in. Yeah. So
sure.
Maybe we can. Yep. So maybe you could start off first, just real quickly, brief description of sort of the lab setup that you're using, so everybody's familiar with that, and then maybe you can start, down some thoughts about maybe tuning or initial sort of setup with Spark.
Yeah, absolutely. So, hi everybody. I do a bunch of the kind of technical architecture work within EMC, and a lot of the focus right now, at least around Hadoop-enabled applications like Spark and things, is primarily on Isilon. And within the lab that we have, of course, we have a number of different Isilon resources, but we also have small dedicated compute clusters, primarily running things like Cloudera, CDH, and using Spark within those distributions, and not typically in standalone mode, to evaluate the performance and just sort of interoperability with Isilon and the different versions of OneFS for that. So largely the things that we've concentrated on have been using OneFS 7.2 because of its support for HDFS up to 2.4 at this point. HDFS 2.6 support is coming by the end of the year. And of course, we recommend using Isilon not just because we're EMC, but also because largely what we see in this industry is Isilon being used a lot to act as sort of a central distribution point for a lot of data. So that it will actually be able to collect your data from all instrumentation and then act as a central clearing point for doing a lot of the computation work and everything that needs to take place afterwards. So having a small compute cluster with running Cloudera or Hortonworks or something that has a complete Hadoop distribution in it, along with things like Spark and Yarn, it works out really well for a lot of our customers and in a lot of setups because you're able to do all these, run things like Atom, run things like Thunder from the compute cluster without having to move your data around or do any significant kind of shuffling or things like that. So what we have in the lab, in addition to some Isilon, a lot of this testing has actually been done with Isilon S210s and Isilon S410s, and results have been fantastic for both. And just a quick note on the way HDFS is supported within Isilon is that the name node and data node are available on any node in the cluster. So such that it provides the same kind of reliable HDFS service that everybody's used to, but it's not done with any kind of direct attached storage. And in the cases of things like Spark, which draw most of their data into memory, it makes fantastic sense. The degree of throughput we're able to get on HDFS on some of the preferred nodes is amazing. There are some benchmarks that we have, at least on the S series, where we've been able to saturate the 10 gig links that we have on the back of these things. So we get close to 8 gigabits per second out of a node using HDFS. So there really isn't much of a performance penalty when using it. And of course, you do save a significant amount of time by not having to stage the data into a directly attached Hadoop storage framework up front. So with things like Spark, in this particular project, we took a look at running Atom, and we took a look at running Thunder, obviously for different types of data and different data sets. For both, we generally focused on using Spark 1.2, and this is largely because of the kind of support matrix that we have around Cloudera versions and things. So given what is directly supported between Cloudera and Isilon and directly integrated between Cloudera and Isilon, Spark 1.2 was the maximum that we could really do. Also, Spark 1.3 introduces some occasional need for HDFS 2.6, which is not officially supported in OneFS until the end of the year in the Riptide OneFS 8.0 timeframe. So 1.2 was the general focus, and obviously it was typically run in cluster mode. For each one of these things, we tend to have to set a lot of these things for each job to set the master. So we just designate one machine as the Spark master. That we take that configuration primarily from the Cloudera setup, and then we are able to at that point to at least within Atom and Atom Submit to be able to provide suggestions when running the job in terms of the amount of parallelism and shuffling that takes place, right? So in terms of the parallelism that we set for the kind of thing, that we do tend to follow the general Spark suggestions and set it to 2 times the number of cores. Although, what we did notice is that there is a point at which you're dividing up the data set into such small parts that actually the total execution time tends to go up, right? So, 2 times the number of cores seems to be the absolute maximum. Backing off of that a little bit also seems to be fine when setting the default parallelism for the entire job. And then in terms of things that are unique to the Isilon and the way that it sets up or serves out HDFS, largely, the biggest thing to do is that we don't need to do any kind of significant shuffling and consolidation of files during a shuffle process, that intermediate shuffling that Spark does in between. So that can actually be set to false and does provide a significant time boost when you do so. The data is not going to get, essentially the data is not going to get any more local if it's shuffled or not, right? So the way it's served out of the Isilon is kind of equal whether it gets rearranged or isn't. So there's no need to do that entire consolidation during a shuffle phase. So there are easy Java options that are set during Spark jobs. In this case, spark.shuffle.consolidate files. They can be set to false. And then that does make it a lot easier, or end up saving a significant amount of time with that. A lot of these options, or all of these options at least, can be set entirely through the Atom Submit script that is available in the Atom distribution. And we do recommend just doing that sort of as a best practice, and then using that script to submit jobs to the entire cluster. It does so via yarn, and then runs everything across the entire cluster that you have set up with that. Typically, in terms of CDH versions, the ones that support Spark 1.2, I believe, are CDH 5.1 and 0.2, and these are the general versions. And of course, there's minor numbers after that, but these are the general versions that should be utilized for something like for these jobs. And in terms of Thunder, the same general thing applies. The general steps apply, in terms of suggestions for parallelism and then shuffling and the need to consolidate during a shuffle and things like that. Also, in terms of network, as you see here and stuff, we obviously do this almost entirely over the 10 gig network that we have set up, and everything's set up with 10 gig as well. And the timings we've been able to achieve on this have been just astonishing and outstanding. The only note that we should have to make is that with Atom, at least, there is a sort of conversion penalty, a step that needs to take place where it takes existing BAM data and converts it into the Parquet format, columnar format that it retains things with. This does take a rather significant amount of time, but it is a step that only needs to be done once for every data set. And then after that, the time savings that you get from subsequent analysis within Atom when using this format more than makes up for the penalty of actually having to convert into that format in the first place. So in general, these are both terrific packages to use, and definitely recommended, and very fast with Isilon in place using Cloudera or Hortonworks on for all of their analysis.
All right. Actually, I think we're at time. The half hour actually went by really quickly. I think Rebecca or Erica, if you can just advance to the next slide, please. Just to really wrap up here, I really want to extend a thank you to Frank at the AMP Lab at Berkeley. He provided us some valuable discussion and background information in terms of the development work with Spark and Atom that group is doing. So thank you very much. And then also Jeremy Freeman at Janelia, he was kind enough to allow us access to some example data sets derived from a light sheet experiment that group did about a year ago. So, many thanks to that group as well for providing that particular data set. All these things are actually, described in papers that I showed earlier. You can definitely find them on, in Nature Methods, or just go visit the AMP Lab, and you can get a lot of detailed information, or go to GitHub as well. So I think we'll wrap it up there. Thank you very much, and until the next webinar, we'll have one June 10th, and we'll have a conversation with some colleagues at VMware about virtual HPC automation. So see you next time.
All right. Well, thanks so much. Again, I want to thank everyone for attending the FIRST Live webinar. I also want to thank our speakers for participating and EMC for presenting. The webinar has been recorded, and you'll be able to access the recording within 24 hours on the same page that you used to register for the event. Thanks again, and we'll look forward to seeing you at